In this video, we're going to be talking more about tournaments. So remember, a tournament is just an oriented complete graph. And we're going to be talking about them in the context of when they are Hamilton or not. So remember that a Hamilton path is a path that visits every vertex, and a Hamilton cycle is a cycle that visits every vertex. So we've talked about these before. But now we want to talk about them in the context of tournaments. So let's just check out this example here in brown. So if this is our tournament T, let me get to black here. If this is our tournament T, does T contain a Hamilton path, and does it contain a Hamilton cycle? So you may want to pause the video and just think about this for a second. We'll go ahead and label these vertices here, V1, V2, V3, V4, V5. So you may want to just check for yourself and see if you think this does or does not. Okay, so path first. It does contain a Hamilton path. For example, we can go V5 to V1, V1 to V4, V4 to V2, V2 to V3, right? And that's a path we're always moving in the correct direction, and we visit every vertex. So let me write that down. V5, V1, V4, V2, V3. And now, does it contain a Hamilton cycle? Well, in this case, based on the choice of our path, we see that it does, right? So we started at V5 to V1 to V4 to V2 to V3, and now this arc is conveniently located for us to close up our cycle. And so again, here the answer is yes, and it's the same beginning as our path, right? And then we just close up this path end to end and go from V3 back to V5, and that gives us our cycle. Well, we'd like to know, when does a tournament have a Hamilton path? When does it have a Hamilton cycle? So that's what the rest of this video is dedicated to figuring out. And it turns out that every tournament has a Hamilton path, which is a little bit surprising. And we're actually going to prove this. So, every tournament contains a Hamilton path. So the way we're going to prove this is we're going to let P be the longest path in the tournament. Okay, so there's got to be one of maximum length, and so we're just going to call that one P. And we're going to say, okay, well, this path is vertex 1, 2, blah, 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 up to K. We don't know how long it is, but just these K vertices make up our longest path. And if the path contains every vertex, then that's fine, right? Because it'll be a Hamilton path, and so the tournament will have a Hamilton path. Okay, so that's like sort of the easy case. So we're going to assume that there's some vertex that's not in our path. This should say P. Right, there's some vertex in the tournament, right, the vertex set of the tournament, that's not in our path. And now what we're going to do is show that we can include that missing vertex. Okay, so let's see what's happening here. Remember, we're letting P be our longest path, and we're going to label it V1 to VK. So here I've got, in green, the sort of situation modeled out. So here I'm just choosing an example so that we can see what we're talking about. But you can see I've got this path V1 to V2 to V3 to V4, and we're going to assume that no matter what the directions are, right, on all these remaining arcs, right, because this is not a tournament yet, there are a lot of arcs that are lacking direction. But we do have what's, quote, our longest path, and it goes V1, V2, V3, V4, and then we've got our vertex V that's not part of the path. Okay, so this one's not supposed to be part of our path. Okay, so now looking over here at the text in blue, if V is not supposed to be part of the path, what two arcs are you not allowed to have in this green tournament? Right, so remember, these are all supposed to be arcs, so we're supposed to put directions on all of these edges that are missing directions. But there are a couple of directions that are not allowed if V is not supposed to be in our path. So you may want to pause and think about what those are. So we cannot have VV1. That can't be an arc, because if it were, then we could just tack V onto the beginning of our path, right? And then this would go in the correct directions, right? If this were an arc, then we would have a longer path, right? We could just start at V instead of starting at V1. Okay, so that's not allowed to be one. And then what's the other one? You're also not allowed to have VKV. So remember, we're talking about our path is for arbitrary k. The example I'm giving in green stops at 4, but we're just doing it for an arbitrary length. So when you go to the end of the path, you're not allowed to be able to just go to your missing vertex, or else that would make a longer path. Right? Okay, so you're not allowed to have that direction. So let me write this back. VKV. Right, so this is not allowed to be pointing this way. So that means that we have to have certain arcs here, right? I mean, if VV1 is not an arc, then that means that V1V must be, right? This thing has got to have a direction, so it's got to be pointing that way. And similarly, if VKV is not an arc, that must mean that VK is an arc, right? We've got to point that way. We wasn't allowed to point that way, but it's got to point some way, so it's got to go like this. Okay, so we've got our longest path, which forces the direction on these two edges. Okay. Well, it turns out that when you have this construction, that means that there's some vertex in your path, right? Some V sub I, so in either V1 or 2 or 3 or 4, there's some vertex where you can go from that one up to V and then come back from V to the next one in the path. Okay, so essentially, let me just show you what this means. Essentially, this is saying that maybe you can go from V2 up to V and come back to V3 and not break the chain in your path, but just include V and then pick up where you left off, right? Or maybe you go from V3 to V to V4, right? And you include V and pick up where you left off. So let's see why that is true. So here I've just copied in red what we had, the configuration we had above. So we've got our V1, V2, V3, V4 path, and now we've got these forced directions on these two edges, these two arcs associated with V. Well, let's just think about what's happening here. Okay, we want some vertex in the path that we're supposed to be able to go to V and come right back down to the next one. Okay, well, if this edge turns into this arc, right, then that vertex is going to be V1. Right? Because then it will be V1V and V2, right? So V1V, V2. And then instead of having this longest path, 1, 2, 3, 4, we could go 1V2, 3, 4, right? Which would be a contradiction because we'd be too long. So that means that this one must go in this direction. Okay, well now let's go to V2. Well, V2, we can go up to V, so if this arc is like this, then we'll be able to go from V2 to V to V3 and pick right back up where we left off. And now we'll have 1, 2, V3, 4, which is again a longer path. So that's not allowed, which means that this one must go like this. And you can keep kicking this argument down the road, right, further and further along your path, except when you get to the end, what's going to happen? So like here, we're already at the end. But what happens, V3 is pointing towards V, but then we know from the very beginning that V was pointing towards V4. So now we have V1, V2, V3, V4 as our longer path. So that's why this statement in green holds, is this argument that I was just talking about down here. So that means we can make a larger path, right? We can make a path P prime where we start wherever, and then at some point at that vertex VI, we can jump up to V and then come back down to VI plus 1, and that's going to give us a longer path. But that's a contradiction. And what is it contradicting? It's contradicting the fact that we assumed that P didn't contain every vertex. So now it has to contain every vertex, but if it contains every vertex, that means that it's a Hamilton path. Okay, so every tournament has to have a Hamilton path. Now, you might want to ask yourself if that's true, whether every tournament has to have a Hamilton cycle. Okay, so by the way, to make this a tournament right, we need a couple of more directions here, but it doesn't matter what they are. Okay, and it turns out that tournaments don't always have Hamilton cycles. So first, before we get to that result, let me mention this one really briefly. Every vertex in a non-trivial strong tournament is in a triangle. Okay, and that's a little bit surprising. So remember, strong means that for every pair of vertices, there's a UV path and a VU path. So, of course, that will mean we have cycles, so this thing is not transitive. And it turns out that being strong is enough to imply that every single vertex is part of a triangle, which is just a 3 cycle, right? A triangle is a cycle of length 3. And we're not going to talk much more about that result. But it's also true, this question about when they contain a Hamilton path. So a non-trivial tournament T is Hamiltonian. Remember, we call Hamiltonian, we say a graph is Hamiltonian or a tournament is Hamiltonian if it contains a Hamilton cycle specifically. Well, everyone contains a Hamilton path, but they only contain a Hamilton cycle if they're strong, right? If and only if. So if you know a tournament is strong, then you know for free that it contains a Hamiltonian cycle. And if you know a tournament contains a Hamiltonian cycle, then you know for free that it's strong. So we're not going to prove this one, but it's still an interesting result. And this wraps up our conversation about tournaments.